1:30 and have. Two times. Well, the evening was leaving home. Whoever was leaving, the guy's like. Yeah. And then. I think you didn't get it. Oh, yeah, I mean, yesterday, because I missed part of the city's negative. I checked the text. Yeah, I had a question about it because how come it's not negative here, but since I checked the textbook for, this is the one that we turn in, right? Well, there's one that's lower where they have negative areas. And I checked the textbooks and the angle was negative. Because the formula is all sine theta plus sine theta. Since you have a negative, that makes the object is negative. So that makes it negative. So yeah, and if you plug that in, then you convert from your polar to the vertical angle, it will get the right number. If they give us units degrees, convert to their units. Which problem I really share to the help right now. That helps us go. This is my question video. When he asks us things, you find the time that the diamond for two numbers. I'm going to remember. Yeah. I was working on this. Run a someone here. I've turned it into K. K has units of so big users from the square of square this this I'm not this I'm going to give it just a picture of the trade. No, I'll be honest. I just the phone call.
Do we ever need to bring that board in here, or is it just for the lab?
Oh, just for you can't even do anything on these computers anyways.
Oh, okay.
Hello.
May have not it was about, so I got a new router like the day before when the very first reading was due, and then I thought it was due like that day, like at night. And
Oh, that's okay.
it was closed. And then I want to tell you about, what was I? Oh, the third reading one. It only has one try. I like went to go do it and like.
Is it the one that's due Wednesday?
Yeah. Or
Friday?
Doing 7 days.
Okay, so next Friday.
Yeah.
Okay, I'll look at it and see if I can change it.
Yeah, I think I thought it was the second one, but I realized this was like I wasn't supposed to do this one yet. But just so you know, it doesn't have multiple tries.
I have 3 minutes right now, so I'll look at it and ask you to try again. once I see if it's changes.
Yeah, I think I just, be wrong. That's.
But this year didn't get shit.
You might not have, but I know I am behind on email. I mean, I am perpetually behind on emails.
I just honestly, when I started the semester, I went through and I deleted everything before like the last 2 weeks, and I was like, I'm just not gonna deal with it.
I sent it.
Okay, so quizzes.
For
So
that, I kept forgetting.
September 8th. Bill,
Oh, no.
But it's like all that money and put it in the same. Like 17.
Yeah, the one chapter 3.1 to 5. Which are ones I noticed didn't have multiple scales.
settings.
Wait, I would get it.
Okay, it didn't save. So unlimited attempts,
I like the wall.
5-minute cooldown.
I don't care.
Try again.
Short is because. Like one class.
I was about to do that, so I was.
My case is.
And then would I be able to- The first one again, or is it two?
I'll just I'll change your thing once I find your email, or if you send me another email.
Yeah, is the plus for your one supposed to be in the subject, or? Did I type it in wrong?
No, you have right. I just haven't.
Okay. All right.
It works.
So you're good in spring.
Yeah, no, I go.
Okay, so it is 9:30 and we can start. I have quite a lot of material I would like to get through today. I am going to be talking quite a lot. The other thing is your reading and your reading quizzes are posted for next week. So it's due Wednesday and Friday because there is no class on Monday. Okay, Monday is Labor Day. Do not show up. If you show up and don't see me, it's because there's no class. Okay. So today I want to cover a bit about VHDL. But before we start, I just want to ask you, Lab 0 setting up went well? Step-by-step instructions? Okay. Yeah.
I downloaded the photo, but I didn't download the entire thing. I got told after that I was supposed to do the entire thing.
You should select the option that has Vitis HLS.
Are you able to like install just that, or do you have to reinstall?
I have never tried doing them individually. I would just uninstall and reinstall with the selection of Vitis. Is how I would do it. I know it takes a long time. When I do it, I just do it overnight. It's overnight. Okay, so basics of VHDL. So for VHDL projects, we have these different components. We have an entity. So this is used to define the external view of the model. What are the inputs? What are the outputs? What are the sizes of the inputs? What are the sizes of the outputs? So this is similar to a function declaration in the .h file for C++. And then we have the architecture section of our VHDL structures. And this is used to define the function of the model. So there can also be multiple different architectures for the same entity. So you can have multiple different implementations. And this would be similar to the function body of the .cpp file for C++. And then configuration. This is used to associate an architecture with entity. So if you have multiple different implementations with multiple different architectures, when you instantiate that entity, you would just specify what is the architecture that you want to use, which implementation. And if you do not have multiple different architectures for that entity, you don't need to specify the configuration because there is only one. It is going to be used by default. Any question on this? Okay, so entity declaration. So this is the main format. Here, let me have this. So you're going to define it. Entity is the keyword, and this would almost always be at the top of the file. And then you can give it an alphanumeric name. So any combination of letters and numbers. And also you can have underscores. Some special characters are omitted and special keywords are also omitted. For example, you cannot name an entity. Okay. And then the keyword is, and then you're going to declare your generics as well as your ports. So for our class, you generally don't need to worry about generics. Generics are how you can make an entity more customizable. Like you can create an entity that is a n bits AND gate, and then the generic that you would change is the n. So it could be a 3-bit AND gate, 4-bit AND gate, things like that. But generally, for the projects that we're making, you don't need to have that kind of customizability. So you can do simple just port declarations. And then you have end entity, repeat your entity name, semicolon. This is how you just declare an entity. All right. So again, any alphanumerical string, and the port declarations are going to describe the inputs and outputs, and we'll talk more about those. And like I mentioned, used as parameters, but yeah.
Do we typically just have one entity? Or
No.
Okay.
So for the first project, yes.
Okay.
But typically no. And also, like, even the later projects were more introduced, so we're going to move like from combinational logic to showing you guys sequential. You might still just have one entity for your project, but as you like do more with VHDL, it'll be more obvious to you when it would be useful to have multiple entities. And I'm actually going to talk about multiple entities in this lecture too. No, it's okay. So port declarations. So they go inside the entity declaration. And again, these are noting your inputs and outputs. So here, you're using the keyword port. And here we're creating signals. So we're creating two, so a clock and a clear. And these are inputs, and they are bit. And then here, we don't put signal, but we're calling this output port. It's also of type bit, Q. And the reason that we don't have to put signal here is because of this note, right? If we don't put signal as the type, it's just assumed that it's signal. And then that's where our end entity is, entity name, semicolon. Right. So here is the structure of your port declaration, right? What class? So that's signal, right? If there's nothing there, the default class is signal. What is the name of that port? So here we have clock and clear, and then Q for outputs. What is the mode? So is it inputs? Is it outputs? And then the type. So in this case, the type is bit. Okay. So the class, what can be done to the object? The name is just the identifier for it. Mode is the direction. And then type is what can be contained inside. Make sense? Okay. And again, if you do not specify the class, it is assumed to be signal. And for the most part, you can just use signal for the purposes of this class. Okay. Okay, architecture. So this is the structure for architecture. So the keyword is architecture. And then you're going to give it a name for the architecture. And it is of, and you need to put your entity name, the entity that this architecture is implementing. And it needs to match the entity name from the entity declaration. So again, architecture name is just name of the architecture. Entity name is the name of the entity that you're implementing. And then after we have all of this and the keyword to start is begin. And the keyword to end is end, and then architecture name. So the begin and end are like your open brackets, close brackets from C++. Okay, so here is a full example. So here we are just importing some libraries. And the reason is that we want to be able to have this type of standard logic. And we'll go over this again today. But here's our entity declaration. So keyword is entity, right? What's this? The name of the entity. And then the other keyword is keyword port. So what is the class of this port? A?
Signal.
Yep, signal, because there's nothing in front to declare otherwise, right? So signal is default. And then we have semicolon. Its mode is, it's an input. And its type is its standard logic. Okay. And then B is the same. It's signal, input, type is standard logic. Y is output, standard logic. And then keyword end, and then entity name. So this is our declaration for the entity. So we know it has two inputs, A and B, and one output, Y. And then this is our implementation. So architecture, and this is the name of our architecture, right? And we're implementing the entity and gates. And then keyword is, and then begin and end. Again, this is your open bracket, close bracket, right? And then you put the end for the architecture name. And this is our implementation. It's very simple. So Y is being assigned A and B. Yeah.
So instead of using a chip, it's just using the ports and software.
What do you mean by using a chip?
So instead of just using like a AND gate chip, like on a breadboard or something, this is just using two ports on that take input and then some
Okay.
software.
Okay. So this is a software description of hardware. So it's a hardware design language. So what happens is this gets compiled into a schematic, and then that schematic is used to program the FPGA, which is programmable hardware.
Okay.
So the FPGA would be configured such that the inputs are connected to an AND gate to the output.
Got it. Okay.
So it's just a description of hardware. That's basically what this is. Yeah.
If it wasn't signal, for example, change the standard logic part, or would it be the same?
So don't worry about the class type. That's why I'm saying just signal is what we're going to use. Okay.
I had the same question.
Okay. All right. So here is a checkpoint. So do answer this on your own. And the code for today is 702. 702.
Two.
702. 702. It's always going to be 3 digits. Yeah. Okay, I think this is a relatively quick question. So is anyone still thinking about this?
Thumbs.
Okay, but do you have an answer in your head of,
Yeah.
okay. Anyone else? All right, so we are not quite at the threshold, but we should, in the interest of time, just go over this together. So let's just go over it one at a time. So standard logic, it goes at the end. And is it defining the signal type? Yes or no? Anyway, yes. Yes, so this is defining the signal type. Does the signal type define whether it is input or output? No, that's the mode. So the mode is before that, right? It could be either in or out or in out. And then is it defining what can be contained in the signal? Here, no, anyone, yes? Yes.
I thought that'd be.
So I'm just going to go back to the, it's just the definition, right? So port declarations, type, right here. It defines what can be contained inside. Yeah. Okay. So basically, what you should get out of this is that what goes at the end of a port declaration is what type of signal it is. And then the type of signal defines what can be contained in that signal. All right, so different signal types. So we saw bit, right? It was the first example that we saw. And bits, they can only contain the values 0 or 1. But as we know, this is not realistic, right? It takes time to switch from 0 to 1. You could switch very rapidly and be undefined. You could just be not connected to anything and floating, right? So bits is useful, but it's not a realistic case. That's why we use and import standard logic. So standard logic can contain many other values other than 0 and 1. So of course we want it to be able to do 0 and 1. We are in digital logic design after all. But now we can know in our design when it's Z, that means it's not connected to anything. It's high impedance. And X is unknown. So this is usually because it's trying to be assigned from multiple different places. Like if you connected the output to an AND gate and an OR gate, and it's connected to the same output, then it's undefined what that output would be, right? So this is why we use standard logic. And for the most part, in this class, you'll make all of your input output ports of type standard logic or standard logic vector. And what do you think standard logic vector allows you to do? Just a guess? Huh? Yeah, so you can have like a multi-bit input, multi-bit output. So if you need multi-bit input, multi-bit output, you use standard logic vector, and you need to define the size of it. So if you wanted a 4-bit standard logic vector, you would say standard logic vector, and then in parentheses, 3 down to 0. So 3, 2, 1, 0. And you can reference that standard logic vector just like you would reference in an array. Okay. There it is, standard logic, but can contain different length values.
How large can vectors be?
As large as the FPGA supports. But in simulation, as large as you want it to be, as long as Vivado does not crash. And for the projects in the class, you shouldn't be making Vivado crash, but you can, projects do get more complex and Vivado can crash. But for our projects, they're very, very small, very small. Okay, so assignments in VHDL. So we use this less than equals when we're assigning to a signal. And we use colon equals when assigning to a variable. And a variable immediately takes on the value assigned to it. And variables must be declared inside a process only and can only be used in that process. And you can think of variables as kind of like local variables to a function, if you're thinking about it from program perspective. But for the most part, we are going to be working with signals. You won't need variables. All of the examples I show, I'm not using variables. Students have used variables in the past. They do work, they are helpful, but I will tell you, they are not necessary. And if you are going to use my slides to help you, you will not see variables in my slides. Okay? So here is an example. So we have QA is going to be assigned R or T. So we can see that that's this branch of the circuit, right? So we have input R, input T, here's an OR gate, and now this is the wire or signal QA. You see that? And then QB, which is the output of our circuit, is going to be G, XOR H, right? So we have G and H as inputs, and this is an XOR gate. And then we're going to NOT that, so invert it, and then take the AND between QA and our intermediate results to get QB. So you see how we can go from this hardware design language to generate the circuit. Okay. And we see that QA is like just an intermediate wire. Okay, so similar to that, if you want an intermediate wire like QA, you need to declare it inside your implementation. So here we have this signal that we're declaring. We're calling it int because it's internal as our example. And it is of type bit. And it does not have a mode because it is not a port. Okay. So in order to assign that wire to be the wire between the end of the AND gates and the beginning of the NOT gates, we assign that int is I1 and I2, right? So I1 and I2. And now int is going to be inverted and sent to the outputs. Okay. So remember, ports, you don't need to specify their signals. They're signals by default. Internal things, you need to put signal. It needs to be declared. Make sense? Okay. So here are operators that we have available to us. So we have logical operators. We can do bitwise not, bitwise and, or, NAND, NOR, XOR, XNOR. All of these are available. You can do comparisons. Is it something equal, not equal, less than or equal to, greater than or equal to? These are important for what we will talk about also in a bit. Behavioral modeling. You can also shift. So if you have a multi-bit standard logic vector, you can shift left logical, shift right logical, shift left arithmetic, shift right arithmetic, and other types of shifts. And you can also add two vectors, subtract. You can concatenate different strings together, different standard logic. So like if you have a 4-bit input, 4-bit input, and you want to make it an 8-bit input, you can concatenate them with the AND operator. I mean, yeah. And you can multiply. You can take the modulus. You can get the remainder. You can divide. And then you can do exponents, absolute value. Make sense? So you have all of these available. All right, so here's a checkpoint. So do this on your own. Yeah, I see a lot of answers moving around, but no, it's really new answers coming in. Are you guys still thinking about this? Okay, so this is very common. And again, I'm just going to go over this all together because we do have a lot to get through. So you guys are split 50-50 for the most part between A and E. So though it's kind of the reason that I show this question at this point is so that you see this mistake all together now, so that you don't make it when it matters more, like in your lab or like on the quiz, because this is a common misconception. We are a hardware design language, not a programming language. So the code does not execute sequentially. This is a description of the hardware circuit, right? So we can reorder this however we want. In the end, the description is the same, right? We are assigning E to be the XOR of A and B, and then F is the OR of C and D. And then those outputs, like those intermediate values, are ANDed together to Y. Okay. So it actually doesn't matter how you order them. So E is kind of just here as make this mistake here. And now you know, and will hopefully remember that it's not like sequential operations. Okay. But does it make sense how it's a hardware design language and like it doesn't really matter what the order is, it describes the data flow still? Okay. So yeah, the correct answer is A, right? So we have A XOR B is E, and then C or D is F, and then if this is E, this is F, we have and that's assigned to Y. Right? Okay, so and this is what we call data flow modeling. So this is what you'll see in lab 1. You're going to be shown different modeling methods. The first is data flow modeling. So this is just describing the combinational parts of the circuit. So how does the data flow through the circuits, right? So here we have the internal signal int that is first going to be assigned the AND of I1 and I2, and then it gets inverted. So it describes how the data flows through the circuits. So if we go back, this is also data flow modeling. Got it? And this is all that we have shown as examples in the slides so far. But now I want to talk a little bit about structural modeling. So we're going to define the functionality with structures and calling other entities rather than through describing what the combinational circuit looks like. So this is going to involve connecting instantiated components to define the functionality of the circuit rather than calling the functions of the AND gates or the OR gates or things like that. So these components can either be modules or entities that you create. So this goes to your question of multiple entities. So you can create these entities and then instantiate them and connect them. Or there are device primitives, like there's and2, or2 in that are predefined entities that you can use as components. So structural modeling is more useful when you have a larger project with hierarchical designs. So like the example I put here is you have an entity that is a 1-bit adder. You can now create an 8-bit adder by instantiating 8 of those 1-bit adders and connecting their ports appropriately. Okay, so that would be structural modeling. So here is an AND gate, structural. So the component that we are going to use is this AND gate. So this is a predefined component, predefined entity, I should say. And what we want to be able to do is make a 3-input AND gate. But our base entity is a 2-input AND gate. So we see this, right? We have two inputs, I0, I1, they're in. One output, oh. Right? So we're going to create these two input AND gates. Okay, so the first one, we're going to get the AND of A and B, so our first two inputs. And then the output is going to go to this internal signal, A internal. That was defined here. And then the second AND gate, the first input is going to be that result of the AND of the first two inputs, and then ANDing with the third input. And then the output of this AND gate is going to be connected to the output of the circuit. Do we see this? Make sense? So if you have any doubts on when you're instantiating an entity, you can come back to this slide. You can see how to connect the input into the input of the port, the syntax that we have. And if you need an internal signal like we do here, aint, you need to define it in the architecture as a wire, essentially. Make sense? Okay. So the last one is behavioral modeling. So this is defining the functionality of the circuits with no specific structure in mind. And there can be multiple different hardware that would be created to implement that behavioral code, but it allows us to write more complex entities faster. Right? We don't need to define a mux. We can just say a mux is basically an if like if then statement. You're just selecting. So you can just write it as behavioral code. It will generate the mux. And if you have a case statement, it will generate a multiple input mux. Okay, so behavioral modeling. So we need to define within the architecture block and inside a process block. So a process is defined to model sequential circuits or combinational circuits. It can be either or. And a process runs when any signal in the sensitivity list has an event or change in value. So this is the sensitivity list. So the process C, D, E. In this case, if C, D, or E change their value, the process evaluates and it updates the outputs based on the behavioral code that you have in the process. And then to synthesize it as a combinational circuit, the process needs to have these two things satisfied. So it has no edge sensitive assignments. So in the process, the sensitivity list, you can't put pause edge or neg edge or things like that. You will learn more about that later on. And then all outputs must be defined for every conditional statement. So every possible condition needs to be met. So if you just have if and then a sign, and there's no else, that will be a sequential circuit, not a combinational circuit. Does that make sense? Do you know what I mean by all of the outputs must be defined by a conditional statement? Okay, so let me just break this down. Oh, if x is greater than 0, say this is the behavioral code unit. Okay. And then a is 0. And this. So this is defined for x is greater than 0. So what about the case when x is less than 0? It's not defined. So in this case, it thinks that your process needs to be a sequential circuit. And if it's not this, then it just keeps A as whatever the previous value was. So then it needs a memory, and that's why it would be a sequential circuit. But if you wanted it to be purely combination, now we're defined for all cases of x. Because if it's this, it will be this. Otherwise, it's this. There's no ambiguity. All of the cases are covered. Make sense now? All right. So here is the first example. If statements. So you have your condition, and then you can have else if for a sequence of them, and then else, and then you have this end if. So here's your example of a mux, right? So we have selector bits, and we have A, B, or C that we want to select from. And then we begin. So if the select A is 1, then the output Q is A. Otherwise, if select B is 1, then Q is going to be B. Otherwise, Q is C. So this is basically a 3-bit, like 3 to 1 mux, right? We have 3 options, only one of them is going to go to the output. But you see how this is behavioral code? You don't have to create the AND and OR gates that are inside these muxes. You don't have to instantiate a 2-bit, 2 to 1 mux and a 2 to 1 mux and connect them. That would be structural. And you can do the same thing with a case statement. So you have select, that is, in this case, it's a multi-bit, so it's 2 bits. And then you have the case. So when 0, 0, it's going to get A, 0, 1, B, 1, 0, C. And then by saying when others rather than 1, 1, we cover the rest of the cases. So if select is undefined or it's high impedance, we have now covered all of those cases by just doing when others and selecting D as the base case. If we just did when 1, 1 and didn't have a when others, we would be undefined for the case of the select signal being undefined or high impedance. So this would become a sequential circuit rather than a combination circuit. Okay.
Are projects usually designed with one or the other type of modeling, or there's mixing depending on what's?
It's almost always mixed.
Okay.
Almost always. But for again, our projects are going to be very simple, but towards the end, especially with the memory lab and the final project, you are going to for sure be mixed modeling. And that's the next style. So mixed modeling. So in this example, we have 3 to 1 mux that we want to create, and we have these 2 to 1 mux modules. So say we have a behavioral description of a 2 to 1 mux as one entity, and then we can create a structural description of a 3 to 1 mux by utilizing 2 of the 2 to 1 muxes that were coded in behavioral. That makes sense? Does this make sense to you guys? How it's mixed? I'm saying that these are implemented with if statements as their own entity. And then in another entity file, you instantiate them as components and connect their wires like this to make this. Okay. All right, so this is another checkpoint, but I think in the intro, we have 8 minutes. So I want to get over test benches. So what modeling concept does this use? We already actually talked about this because this is the same example code from before, right? This is anyone? Look at the slide. Data flow. This is data flow, right? We're not instantiating components and connecting them with wires. We are using the AND gate descriptions. Okay, so test benches. So they are going to be a major component of all of your projects. You are going to be writing your own test benches. So the components of a test bench, it is going to be an empty entity. So an entity with no ports. Okay, and it will be a separate file. And that's going to be the top level structure. And then in terms of internal signals, you're going to create signals for the inputs of your component that you're testing, as well as the outputs of the component that you're testing. And then you're going to declare the UUT. So this is unit under test. That is the entity that you are trying to test. And you're going to connect your internal signals that you created to that entity that is under test. And you're going to generate inputs for that entity, essentially. So like if you have an AND gate, a 2-bit AND gate, so I have 2 inputs, 1 output. I'll make an input A, input B, output Y, right? Connect A to the first port, connect B to the second port, connect Y to the output of the AND gate entity. And then when we write the procedural block, we will test it by saying A and B are equal to, say, 0. Both of them are 0. And then we'll add a wait statement. And then when we run the simulation, we should see in the waveform, when the inputs are both 0, it's an AND gate. Y should be driven to 0 and 0 is 0. Okay. So we will stimulate the inputs, look at the waveform to see what the output becomes. And I'll show you examples. So here is an example test bench. So here's the entity declaration. Like I mentioned, it's empty, right? No ports. So entity, that's the name. And then keyword is and entity name. And then we have to make this architecture that is the implementation of our test bench. And in this, we are testing this component FSM. So FSM is some other file, some other entity that we have implemented, and now we're trying to test it. And it has clock, inputs, outputs. So we are going to create these internal signals. So we have clock, input, output. And then this is our unit under test. We're connecting clock to clock, input from test bench to input, and output to output. And this assignment is just the default assignment. So when the simulation first starts, it's going to be already 0 for the inputs. And then the reason that we have this process is because this is going to be a sequential circuit. So we need a clock. So now every 10 nanoseconds clock is going to change. It's going to become the opposite of clock. So it has a period of 20 nanoseconds, right? And then below that, we have our process block for our test cases. So we wait 5 nanoseconds. First test case is input is 0. And we can see here is 5 nanoseconds. And remember, input default was 0 from before. Right? So at time 0, it was 0 already. So for here, it stays at 0. And then we wait 20 nanoseconds. So now at 25, our next input again is 0. So it doesn't change. And then our next input is going to be 0. So at 45, but then our next input after 20 more nanoseconds is 1. So you see it change to 1 here. Do we see this? Okay. And for 1 full cycle, 20 nanoseconds, it stays as 1 and it goes back to 0. But what is important to see here is we can see the clock, right? We can see the other input, which is our input that we're driving here. And we can see the outputs and how it's behaving. So like for your AND gates, if you saw 1 second, 0, 0, you would expect 0. Okay, question. It's all the same file. So like this is the top part of the file. This is the next part. And this is the next part. Yeah. And I'm giving you a sequential one as an example so that you know how to make this. But for your combinational ones, you don't need this. You'll just need this process block. And you can have their different test cases here. Okay, so we are out of time. We can talk briefly about good practices for test benches on Wednesday.